Good morning. Today, I'd like to talk about the third of our work type problems. This one is a little bit less direct than the other two. In those, for instance, Hooke's law, we had an explicit statement that the force was a constant times displacement from equilibrium. In the second, Newton's law of gravity, we had the statement that the force was a constant divided by the square of the distance center to center. In this last example, we have a slightly more convoluted situation. I want to imagine that I have some flat circular object with a certain amount of area. I'm going to move that object at right angles to the circle a distance delta x number I. The volume of the resulting shape is the area times the perpendicular height. If I already had some volume, this would be the amount by which the volume changed. So naturally, I'll call it delta capital V number I. Shortly, I'm going to imagine that this is the face of a piston head, that there will be a piston cylinder containing some gas. The gas is going to push this, displace it in distance by delta xi, and I'd like to know how much work was done doing that. I need to know two additional facts. One, I need to know something that's going to play the role of our force laws in our previous examples, but because of this convoluted situation, I have to have something that connects the force to something in the law that corresponds to the force laws. If I have some gas that's trapped within a closed container, there's a relationship between the pressure and volume of it. The pressure times volume needs to be a constant. I am lying a little bit here, but this is the way people usually talk about these things. This is going to basically play the role of Hooke's law or Newton's law of gravity. But I have a problem. I need to know about the force. Instead of thinking of multiplying delta xi by the number pi times a, I'm going to think of taking pi and multiplying it by the number a times delta x number I. The reason that I want to do this is a times delta x number I is the amount that the volume changed during this particular part of the expansion. Adding up those estimates, taking the limit as delta x goes to 0, which means all of the delta v's go to 0 also, I find out that the work is going to be the integral of the pressure with respect to volume. I'm integrating with respect to volume. The limits of integration need to be the volume at the start of the situation and the volume at the end of the situation. I'll call those volumes V1 and V2. At first glance, this doesn't look too promising because I have variables P and I'm trying to integrate it with respect to variable V. This is where I bring in that fact that relates the pressure to the volume. And so at this point, we're exactly at the same place we were at for Hooke's law or for Newtonian gravity. If we can figure out what the K is in a given situation, we'll be able to do this antiderivative. We'll put in the initial and final volume, and we'll know the amount of work. Let's look at an example of this. In a spirit that's similar to the kind of things we've done before, suppose that you have a gas It's contained within some container. It has pressure 100 pounds per square foot, and volume is 10 cubic feet. Suppose that that's allowed to expand until its volume is 20 cubic feet. How much work was done? As before, there's a sentence and there's a question. The sentence gives me enough information to figure the K in our pressure times volume equal K law out. Once I know that, I ought to be able to answer the question in a direct way. Given the starting situation, where P is 100 and V is 10, since P times V is supposed to be a constant, that constant must be equal to 100 times 10, which is 1,000. Since pressure times volume is always supposed to be 1,000 for this problem, pressure must be 1,000 divided by the volume. If I put the fact that pressure is 1,000 divided by the volume into this formula, and put in the fact that the starting volume was 10 and the ending volume was 20, the amount of work done is the integral from 10 to 20 of 1,000 divided by V dV. Except for the strangeness of the name of the variable, this is something that you could have done back in Calculus 1. The work done is 1,000 multiplied by natural log of 20 minus natural log of 10. You could use properties of exponents and logarithms. Natural log of 20 minus natural log of 10 is the natural log of 20 over 10, natural log of 2. Multiply that by 1,000. The amount of work done is 693.147 foot-pounds. There are a number of variations on a theme that we could look at, but I think this is enough to get the point across. This entire section of work that we've been doing, applications of integrals, has been to illustrate that integration is actually a very versatile thing. It might represent area under a curve like we're used to, or it might represent a volume of revolution. It might represent arc length. It might represent work. There are many things you can do with integrals, but at the moment we are hampered. The set of things that we know how to find antiderivatives of is relatively small, so our next major task is going to be to make our bag of tricks for integrals bigger. But don't forget, we have a reason for that. We use integrals in all kinds of applications. It would be nice to be able to do lots more kind of integrals. I hope everybody has a good day. I'll talk to you again soon.